NENOMATICA, where mathematics meets YouTube excellence. Welcome to our lesson on converting expressions to perfect square binomials. This is an important skill in algebra that helps us factor and simplify complicated expressions. Before we solve specific examples, let's remember the pattern of a perfect square binomial. The first pattern is a plus b squared, which equals a squared plus 2ab plus b squared. And the second pattern is a minus b squared, which equals a squared minus 2ab plus b squared. Notice how the middle term in each case is 2 times a times b with either a plus or minus sign. This is the key pattern we'll be looking for. Now, let's look at our first example from the exercise. We need to fill in the blanks to convert 4x squared minus plus y squared into a perfect square binomial. Let's break this down step by step. First, we identify that 4x squared can be written as 2x squared, as the square of 2x. And we have y squared, which is already a square. Looking at our pattern, we need to figure out what the middle term should be. If it equals 2x and b equals y, then the middle term in a minus b squared would be negative 2ab, which is negative 2 times 2x times y, or negative 4xy. So our completed expression is 2x squared minus 4x y plus y squared, which matches the pattern of 2x minus y quantity squared. Let's verify this with the steps shown in the exercise. We start with 4x squared minus plus y squared. We rewrite this as 2x quantity squared minus plus y quantity squared. We expand this as 2x quantity squared minus 2 times 2x times y plus y quantity squared, which gives us the final form, 2x minus y quantity squared. Now, let's move on to our second example. We need to convert 9, a minus 6 square root of ab plus into a perfect square binomial. For this example, we need to work backward. First, we recognize that 9 is 3 square root of a quantity squared, as 3 square root of a times 3 square root of a equals 9a. We also see that the middle term is negative 6 square root of ab. For a perfect square pattern, this middle term should be negative 2 times a times b. If we let it equal 3 square root of a, then we need to find what b equals by looking at the middle term. From negative 2a, b equals negative 6 square root of ab. We can determine that b must equal square root of b. Now we can find the last term, which must be b squared, or square root of b squared, which equals b. So our complete expression is 9 a minus 6 square root of ab plus b, which equals 3 square root of a minus square root of b quantity squared. Welcome to this video where we'll learn how to use the binomial square formula to find missing terms in equations. The binomial square formula is one of the most important formulas in algebra and helps us expand expressions quickly. Let's start by understanding the binomial square formula. For any two terms a and b, we have two important patterns. The first pattern is a plus b squared equals a squared plus 2ab plus b squared. The second pattern is a minus b squared equals a squared minus 2ab plus b squared. Notice that the only difference between these formulas is the sign of the middle term. Now, let's look at our first example. We need to find the missing term in the expansion of x minus 6, y squared equals x squared minus blank plus 36, y squared. For this example, we'll use the square of a difference formula. Let's identify our terms first. In this case, a is x and b is 6y. Now, we can substitute these values into our formula. We get x squared minus 2 times x times 6y plus 6y squared. This simplifies to x squared minus 12x, y plus 36, y squared. So the missing term is negative 12xy. Let's move to our second example. We need to find the missing terms in the expansion of ax minus 3 squared equals blank minus 6ax plus blank. Again, we'll use the square of a difference formula. Let's identify our terms. In this expression, a is ax and b is 3. Now, let's substitute these values into our formula. We get ax squared minus 2 times ax times 3 plus 3 squared. This simplifies to a squared x squared minus 6 ax plus 9. So the missing terms are a squared x squared and positive 9. Let's look at our final example. We need to find the missing terms in the expansion of x squared minus yz squared equals x to the 4th power minus blank plus blank. This example also uses the square of a difference formula, but with more complex terms. Let's identify our terms. Here, a is x squared and b is yz. Now, we substitute these values into our formula. We get x squared squared minus 2 times x squared times yz plus yz squared. Simplifying this, we get x to the 4th power minus 2x squared yz plus y squared z squared. So the missing terms are 2x squared yz and y squared z squared. Welcome to this mathematical tutorial, where we'll learn how to express a quadratic expression as a sum of perfect squares. In this case, we'll decompose the expression for a squared plus 4b squared plus 4ab into a sum of 4 perfect squares. Let's begin with our expression. We want to decompose for a squared plus 4b squared plus 4ab as a sum of 4 perfect squares. The goal is to rewrite this expression in a form that clearly shows it's a sum of squares. Let's start by considering what happens when we take 3 times the square of a plus b plus the square of a minus b. 3 times a plus b squared gives us 3 times a squared plus 2ab plus b squared. The term a minus b squared expands to a squared minus 2ab plus b squared. When we add these expressions together, we get 4a squared plus 4b squared plus 4ab, which is exactly our original expression. Now for step 2, we'll further break down the expression. We know that 3 times a plus b squared can be written as a plus b squared plus a plus b squared plus a plus b squared. In other words, it's the sum of 3 identical perfect squares. So when we combine this with our previous step, we can write 4a squared plus 4b squared plus 4ab as the sum of 4 perfect squares. A plus b squared plus a plus b squared plus a plus b squared plus a minus b squared. Let's visualize what this decomposition means geometrically. Imagine we have 4 squares. 3 of them have sides of length a plus b, and 1 has sides of length a minus b. The total area of these 4 squares is exactly equal to our original expression for a squared plus 4b squared plus 4ab. This geometric interpretation helps us understand why this algebraic identity works. Fade in. Now, here's a quick challenge for you. Try to verify that the 4-square decomposition we found is correct by expanding each term and adding them up. Pause the video and try it yourself. In this video, we'll solve a mathematical expression involving square roots. Let's look at the following example. We need to find the result of the expression square root of 2 plus square root of 3 minus square root of 2 minus square root of 3. Let's call this expression. So a equals the square root of 2 plus square root of 3 minus square root of 2 minus square root of 3. To solve this problem, we'll use a strategy of squaring both sides to eliminate the radicals. First, let's calculate a squared. We'll square both sides of our equation to eliminate some of the radicals. This gives us a squared equals the square of the square root of 2 plus square root of 3 minus the square root of 2 minus square root of 3. Remember that we can expand the square of a difference using the formula a minus b squared equals a squared plus b squared minus 2ab. Applying this formula to our expression, we get a squared equals the square root of 2 plus square root of 3 squared plus the square root of 2 minus square root of 3 squared minus 2 times the square root of 2 plus square root of 3 times the square root of 2 minus square root of 3. Now, let's simplify the squared terms. When we square a square root, we get the expression inside the square root. So, the square of the square root of 2 plus square root of 3 equals 2 plus square root of 3. Similarly, the square of the square root of 2 minus square root of 3 equals 2 minus square root of 3. So far, our expression becomes a squared equals 2 plus square root of 3 plus 2 minus square root of 3 minus 2 times the square root of the product of 2 plus square root of 3 and 2 minus square root of 3. Let's simplify further. The terms 2 plus square root of 3 plus 2 minus square root of 3 combine to give us 4 because the square root of 3 terms cancel out. Now let's look at the expression under the square root, the product of 2 plus square root of 3 and 2 minus square root of 3. This is a difference of squares formula. Using the difference of squares formula, a squared minus b squared equals a plus b times a minus b. We can see that the product of 2 plus square root of 3 and 2 minus square root of 3 equals 2 squared minus square root of 3 squared. 2 squared is 4, and square root of 3 squared is 3. So, the product simplifies to 4 minus 3, which equals 1. Now, the square root of 1 is simply 1. So our expression becomes a squared equals 4 minus 2 times 1, which equals 4 minus 2, which equals 2. Now that we have a squared equals 2, we need to find a. Taking the square root of both sides, we get a equals plus or minus the square root of 2. However, we need to remember that in our original expression, we're dealing with real values. Since the original expression, a is the difference of two real values, a can be positive or negative. To determine whether a is positive or negative, we could substitute our answer back into the original expression. Or we can note that since the first term, square root of 2 plus square root of 3, is larger than the second term, square root of 2 minus square root of 3, our answer, a must be positive. Therefore, a equals the square root of 2. To verify our answer, we could substitute the square root of 2 back into the original expression and check if the equation is satisfied. But for now, we'll accept that our answer is correct. Let's think about what we've learned. We used several key techniques to solve this problem. First, we squared both sides to eliminate the radicals. Then, we used the difference of squares formula to simplify the expression. Finally, we took the square root and determined the sign of our answer. In summary, we found that the expression square root of 2 plus square root of 3 minus square root of 2 minus square root of 3 equals the square root of 2. These types of problems involving square roots can often be solved by squaring both sides and using algebraic techniques to simplify the resulting expressions. Today, we'll simplify a complex expression involving square roots. The expression we need to simplify is the square root of 3 plus 2 times square root of 2 minus the square root of 3 minus 2 times square root of 2. Let's begin by examining what's inside each square root. For the first term, square root of 3 plus 2 times square root of 2, we can recognize that this is a perfect square of the form square root of 2 plus 1 squared. Let's verify. If we square root of 2 plus 1, we get square root of 2 squared, which is 2, plus 2 times square root of 2 times 1, plus 1 squared, which is 1. This gives us 2 plus 2 times square root of 2 plus 1, which simplifies to 3 plus 2 times square root of 2. Similarly, for the second term, square root of 3 minus 2 times square root of 2, we can recognize it as square root of 2 minus 1 squared. To verify, squaring square root of 2 minus 1 gives square root of 2 squared, which is 2 minus 2 times square root of 2 times 1 plus 1 squared, which is 1. This gives us 2 minus 2 times square root of 2 plus 1, which simplifies to 3 minus 2 times square root of 2. Now that we've recognized the perfect squares inside each radical, we can simplify the first square root. Since 3 plus 2 times square root of 2 equals square root of 2 plus 1 squared, the square root of this expression is simply square root of 2 plus 1. For the second square root, we have square root of 3 minus 2 times square root of 2, which equals square root of 2 minus 1 squared. So, the square root of this expression is the absolute value of square root of 2 minus 1. We need the absolute value because square roots always give non-negative results. However, since square root of 2 is approximately 1.41, which is greater than 1, square root of 2 minus 1 is positive, and we can remove the absolute value symbols. So, our square roots simplify to square root of 2 plus 1 and square root of 2 minus 1, respectively. Now, we're ready for the final step. Let's substitute these simplified expressions back into our original expression. We have square root of 2 plus 1 minus square root of 2 minus 1. When we combine like terms, the square root of 2 terms cancel out, and we're left with 1 plus 1, which equals 2. So, our final answer is 2. Welcome to this math video. Today, we're going to prove the identity for the square of the difference of two terms using a geometric approach. This is the formula. A minus b squared equals a squared minus 2a plus b squared. Let's start by visualizing this identity geometrically. Imagine we have a square with sides of length a. The area of this square is a times a, which is a squared. Now, let's subtract a smaller piece from this square. We'll subtract a smaller square with sides of length b. But instead of just removing a random small square, we'll do this in a way that helps us understand the formula. Let's divide this large square into regions that will help us understand the formula. Here's what we're going to do. We'll divide it into 4 regions. Now, let's analyze the areas of each region. This blue square has sides of length a minus b, so its area is a minus b squared. These two green rectangles each have area equal to b times a minus b. So together they contribute 2 times b times a minus b, which equals 2 of minus 2b squared. And finally, this red square has sides of length b, so its area is b squared. Now let's add up all these areas to get the total area of the original large square. We have a minus b squared plus 2 of minus 2b squared plus b squared. Simplifying, we get a minus b squared plus 2 of minus 2b squared plus b squared equals a minus b squared plus 2 of minus b squared. And this equals a squared minus 2 of plus b squared. But we know the original area was a squared, so this proves that a minus b squared equals a squared minus 2 of plus b squared. And that's our geometric proof of the identity a minus b squared equals a squared minus 2 of plus b squared. This visual approach helps us understand why the formula works, rather than just memorizing it. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.